Hello. We're going to start talking about greedy algorithms this week, but before that, I want to give an overview of the topics that we've done so far. I want to use this lecture to consolidate a little bit. So I'm going to be talking about greedy algorithms, sure, but I'm going to go through one example, and I'm going to throw everything we have so far at it. We're going to try to solve this using brute force. We're going to try using dynamic programming, and finally, we're going to talk about using greedy on it. Okay, because we've done brute force and we've done dynamic programming. So I thought, well, let's do more brute force and let's do more dynamic programming, because the problem that we're doing, we can also use brute force, we can also use dynamic programming. So again, this week is about greedy algorithm, and this is again based on the textbook CLRS chapter 16. You see, like chapter 15 and chapter 16, they're kind of closely related because they have this thing called optimal substructure. So I'm basing week 4 and week 5 on those two chapters, chapter 15 and chapter 16. Next week we're going to be doing define and conquer, but really define and conquer is just the idea of like breaking down your problem into subproblems, and we've done that. So next week the define and conquer is not about, well, it's not about explaining what define and conquer is, because you already know. Next week define and conquer is about finding complexity. Just remember that brute force, dynamic programming, and greedy algorithm, they're all about define and conquer. Right? As I mentioned before, you have the original problem, you break it down into subproblems, and if you're doing brute force, you just go through all of them. Right? You try to find the optimal one. If you have dynamic programming, you still go through all of them. It's just that every now and then you see, oh, something like H here. If I go to B, I have to go to H. If I go to C, I have to go to H. So might as well just compute it once and store it. So if I do that, all this M, N, O, P, I don't have to compute more than once either. That's dynamic programming, and it's still define and conquer. So greedy algorithm is a bit different, because with greedy algorithm, you kind of make the choice which is the best at the moment. I kind of like calling it the short-sighted algorithm. Like, you don't care about the future, you just do what's best now. And the two terms that we're going to use when we talk about greedy algorithm is local optimal and global optimal. So local optimal is the optimal choice based on what you know at this time. Like, you're at one stage of the algorithm, you have to make a choice, and you just pick one that you think is the best right now. So let's say you want to go from A to F in this graph here. You want to go from A to F, you have three options. You go directly to F, or you go to C, or you go to D. When you're at A, you only know how much it costs to go to C, how much it costs to go to D, and how much it costs to go to F, 10, 15, and 3. So the local optimal here is going to C. That's the cheapest. Like, you don't know anything else. Okay, that's the local optimal. Now, global optimal is different. Global optimal is the actual choice that will give you the optimal answer, like the overall optimal answer. For example, in this graph here, what if it actually costs 14 to go from C to F, and it costs 3 to go from D to F? The cheapest route to go from A to F is actually going through D, A, D, F. That costs you only 13. So that's the global optimal, to go from A to D and go from D to F. Well, if you limit yourself to just this, just A, D, C, then the global optimal is still A to D, because that's the path that will give you the best answer. But the local optimal is 3, going from A to C. So you see how with greedy algorithm, we can say that this algorithm will choose the local optimal and hoping that the local optimal is also the global optimal. I hope that makes sense. It's very easy, right? So I'm going to choose the local optimal, and I hope that the one that I chose is actually part of the optimal solution. It may be the case, it may not be the case. So in terms of coding, actually, greedy algorithm is very easy to do, which is why I'm not going to make any assignment based on greedy algorithm. You can do it in like an hour. There's no point. But in terms of theory, greedy algorithm is the hardest one. You see, you have to justify why you can choose the local optimal, and it turns out to be the global optimal. Remember, if a greedy algorithm works, that means you have to give me the optimal solution, right? If you perform the greedy algorithm and it doesn't give me the optimal solution, then that's just wrong. Like, that's not the right algorithm to apply. You can't use greedy algorithm on it. So if you have a problem where you can apply the greedy algorithm, right, then you have to be able to justify that when I pick a local optimal, that is actually also the global optimal. Like, I know, like, it's like magic. Well, it's not magic because you have to prove it. But that's why greedy algorithm is hard. Because when you're using brute force, what do you have to do? You have to generate all possible subproblems. That's it. There's nothing more to it. You don't have to argue anything. Because you have to argue that I can generate everything. You can generate all subproblems, sure. But if you have generated all the subproblems and you're telling me that you go through all of them, what is there to prove? Nothing. What about dynamic programming? Same thing. You just generate every single possible case, and then as you go through it, you also say, well, look, this one and that one is overlapping. They're the same subproblem. So what I'm going to do, I'm going to store it somewhere. That's it. Right. So again, I mentioned that dynamic programming is basically just brute force. You have to do a few extra things. Sure, you have to show that there exists an optimal substructure in the problem. You have to find the recursive relationship. And yeah, they're not trivial, sure. But the idea is still simple. It's still you going through every single possibilities in a way, right? Greedy algorithm, on the other hand, is different because you're not going to go through all subproblems. So let's say subproblem O. Let's say that contains your optimal solution, or that would be part of your optimal solution. If you are using brute force, you will have to go through all of them to identify a subproblem O as part of the optimal solution. Doing dynamic programming, you still have to go through all of them again. In a smarter way, sure, but you have to go through a lot of subproblems to get to O. You know, greedy, you just magically know, oh, if I go from the top to the subproblem C, I will go to H, I will go to O, and bang, I have my optimal solution. I keep saying magically, yeah, right, but it's like so fast. Like I can just I know which way to go, and I can prove it that I'm on the right path. And I kind of like greedy algorithm. Why? Because you've been solving problems for some time now, and I'm sure you came across a situation where you got a problem, and you don't know how to solve it, but you're thinking, look, if I just pick the best option now, I think I'm gonna get the right answer. Okay, so and then you apply. So not just talk about programming, but talk about real life, right? You have some problem and you're not sure what the best way to do it, but then you just choose the best option now. Like, let's say, I don't know, like you want to pay someone with some coins, right? And you gotta pay someone some amount of money, and you start picking the largest denomination every time. You pick, I gotta pay someone's $4.70. So you pick, all right, I'm gonna pick $2. So I'm gonna pick $2. I wanna pick 50 cents, 20 cents, because that's the least number of coins, and it just works. Why does it work? So those kind of things, like there are problems where I'm just gonna choose the largest one. I'm gonna choose the smallest one. I'm gonna do something which I think is the best thing to do right now, and it turns out, oh, that is actually the way to do it. That actually is the best solution. But why? How does this work? Can I be sure that that's the best solution? And that's what greedy algorithm is. it's like saying that, yeah, you can go choose the local optimal. You can choose what you think is best right now. And then you can prove that that is the best way to do it. So all these doubts that I have when I'm solving a problem, that as soon as I can prove that this is correct, all those doubts will go away. And to me, that's great. That's why I like greedy algorithm. Well, I like this topic. I like the fact that I can prove that what I'm doing is correct. Sorry, I'm rambling a bit here, but hopefully you feel the same. We're going to see some problems that you have seen before in Competitive 5, which are actually greedy algorithm, and we're going to show that, hey, it's actually correct, which I think is kind of cool. But the main problem we're going to do today is more rod making. So look, if you're up to week 5, then I hope you've seen the videos from week 4 and before. And we talk about rod making when we talk about the brute force algorithm. So you got a bunch of rods of different lengths, and the question is, can you make a rod of certain length? Right? This was the tree that I had. You got rods of length 50 to 18, 11, 9, and so on. Can you make the length 27, for example? Okay, and we discussed this in week 3. We discussed this when we talked about brute force algorithm, and including some stupid like, oh, I'm gonna pick 50, I'm gonna pick 2. Then we talked about branch and bound, if you remember. So if you pick 50, you're not going to continue going down this path. You're just gonna stop because, well, L is equal to negative 23. All right, there's no point going on. That's your like bounding function. So if you don't pick 50, you pick 2, and you can go on well for a while longer. You pick 2, you pick 18, you pick 11, and so on. Right, so that's brute force. And can you use it dynamic programming? Yeah, you can. It's not that easy to see, but you can. But let's try this greedy algorithm. So to make it simpler, like the paying someone with coins example that I had. You want to pay someone, so you pick the largest coins every time. Let's sort this. Let's sort according to the length of the rods from longest to shortest. So if you're doing greedy, and you gotta make up 27, which one do you take? Well, you're gonna try to go to 0 as fast as you can. So you're gonna pick 23. So you go ahead, you pick 23. You end up with 4, right? You have to make now you have 4 left to go. And then you realize the next smallest one is 2. Right, if I pick 2, I have 2 left and I'm stuck. If I don't pick 2, I got 4 left, I'm also stuck because there's nothing smaller than 2. So no, that's a dead end. Right, you go back up. This time, like, okay, let's not pick 23. Let's go pick 27. Sorry, not 27. Let's go pick 18. So you pick 18, you got 9 left. Oh, there's a 9 there. I'm done. Cool. Pick 9. Happy. Now, but I want you to know, this is not a greedy algorithm. This is some sort of heuristics for the brute force. And you're still using, what do I call it? It's like using a greedy heuristic on the brute force algorithm. So me sorting it from the largest to the smallest, that's kind of putting greedy there in the sense that, oh, let's pick the biggest value all the time. But you're still doing brute force. If this was greedy, the idea of greedy is you only make one choice. You don't backtrack. You just keep on going forward. And here, greedy just doesn't work. Because greedy, you pick 23. That's the best solution, right? You hope that's the local optimal. You pick 23, you pick 2, and then you say, I can't do it. I'm done. That's greedy. Remember, greedy doesn't go through all the sub-problems. Right? That's what I'm saying here. So if you do backtrack and you keep on trying different combinations, that's still brute force. The greedy algorithm, when it works, you make one choice, you go all the way to the bottom, and you find your solution. That's greedy algorithm. You just go down one path. I guess one way to think about this for me is, if there's no solution in the tree, will you actually still go through every sub-problem. I mean, how do you know that there's no solution? You go through everywhere, right? If you do that, then that's just brute force. That's not greedy algorithm. Even though it does have greedy heuristic, it's not greedy, it's brute force, because you are still going through everywhere. Okay, I hope you agree with me there. So here, greedy doesn't work. Actually, I'm gonna change the problem now, because I want to have a problem where greedy actually works. So now, instead of having metallic rods of certain lengths, well, we still have metallic rod of certain lengths, but you have an infinite number of metallic rods. It's still the same question. Can you make a rod of certain size? All right, so here's the more formal definition of the problem. So I give you an array B, B1, B2, Bn. You got n rods, and I give you an array L. Sorry, I give you an integer L, and you gotta make L from these combinations of B1, B2 up to Bn. Right? So it's the Ci is here. That's the number of Bi that you're using. You can use one rod more than once. So if I give you 150, 25, and 1, can you make 265? Actually, this is going to be an optimization problem. So not only do I ask you, can you make 265, I'm going to ask you, what is the minimum number of rods that you need to make 265? And let's just start by define and conquer. Let's talk about all the different techniques that we've learned. Like I mentioned at the start, we're going to try everything, right? If you do this with define and conquer, and let's make it very simple. Let's say that I call this problem F. So F265 is going to give me the minimum number of rods required to make a rod of length 265. That's what F means. Question 1. How do you break down the problem into subproblems? So you got F265 at the start. Are you gonna do it like this? So if I have to make 265, I have to make a rod of length 265. What I'm gonna do is I'm gonna ask, can I make a rod of length 132 and make a rod of length 133? A bit like boundary search, like divide and conquer. And if I want to make a rod of length 132, I'm gonna make 2 rods of length 61. Right? I mean, that is divide and conquer, right? Is that the right way to do it? Well, I can. Like the answer is going to be 50 plus 50 plus 50 plus 50, because you got when you got 61, you're going to need a rod of length 50 and an 11 rods of length 11. 50 plus 11, 50 plus 11, 50 plus 12. That's a lot of rods. Sorry, I had coins there, supposed to be rods, because this is actually the same problem with the coin changing problem. So you want to make rods of certain length. It's the same thing as you want to give someone money. Like you want to give someone $1.20, and you work out how many coins do you need. Like how many coins do you need to represent $1.20? Well, you just need $2, and 20 cents. But anyway, if I try to do this kind of divide and conquer, if I do this kind of breakdown, I'm going to need a lot of rods. And this sounds stupid, right? You're not going to do it like this. But this is actually interesting. Like you can see that doing divide and conquer like this is very stupid. Like you won't do it like this. You will have like you will pick 100 for sure. Just like the way with coins, you try to pick the biggest denomination that you have. But this one is easy to see. And sometimes with brute force, the difficulty is working out what kind of subproblems. Like how do I break down from the problem into subproblems? It's one of the reasons why I ask you the Lego stairs question for this week's submission on dynamic programming. If you think about that question, you might have something similar, like in a way that I have a problem. How do I break it down into different subproblems? So again, this may be obvious to you that this is just not how the way you do it. But sometimes when you have a problem and you don't know how to break it down, you will try to half it somehow. And this is showing you that you can be led into a wrong path if you do it that way. Yeah, sorry, again, that's pretty abstract, but hopefully that can be like a useful hint if you have to do some problem solving. Just be careful how you divide your problems into subproblems. Anyway, so let's not do that kind of like breakdown. If you're doing brute force, what do you do when you do brute force? Are you gonna try every single combinations? So what, are you gonna try 1 plus 1 plus 1, which just equals to 3? Are you gonna try 1 plus 1 plus 1 plus 1 plus 1? Are you gonna like try to pick 1 and then try every combination of like different numbers of 1s? You're not, right? Because you need 265 of 1s. So if you got 1s in there, well, you're not gonna try less than 265 if it's all 1s. I mean that's what I mean by all possible combinations, right? How many hundreds are you gonna try? You're not gonna try more than 3 100. So this is probably a better way to break down the problem into subproblem with brute force. Remember, brute force, you're gonna try every single combination. So here's what I have. I start with 265. At every point, I have 4 options. I can pick 100, I can pick 50, 25, or 1. If I pick 100, my subproblems is going to be reduced down by 100. So my original problem is F265. I pick 100, now I got to do F165. If I pick 50, I got to do F215, and so on. Right? So this is a much better breakdown than what we had earlier with the like something like binary search. Okay, so on every level, you pick 100, or you pick 50, or you pick 25, or you pick 1. Now, can you use branch and bound? Yeah, if you pick 100, then you pick 100 again. You're not going to pick 100 for a third time, right? Because you pick 100 twice, you got 65 left. Well, you're not going to be able to pick 100 again. So that's your bounding function there. Are you going to try 1, 1, 1, 1, 1, 1, so on? Well, probably not, because let's say you pick 50, you pick 50 again. Let's say you pick 50 5 times, you got 250, and then you pick 1 15 times. So how many coins is that? 15 plus 5, 20 coins. You got 20 coins. So when you go down to this branch, you're doing 1, 1, 1, 1, 1, 1, 1, and you got up to like 21 coins. You just say, all right, that's it, stop it. Like I got a solution with 20 coins, so why am I going through like 21 coins and so on? Like, no, stop it, don't do it anymore. Right? So you can do brute force, and there's this branch and bound that you can apply it to it. Next, can you do the dynamic programming? Are there overlapping subproblems? Yes, there are. If I pick 50 twice, I'm going to have to make 115. And then it's like asking what's the minimum number of coins that I keep saying coins, sorry. What's the minimum number of rows that I need to make 115? But that's the same as me picking 100 once. And that's the same as me picking 25 4 times. So you do have overlapping subproblems. So you can use dynamic programming here. But with dynamic programming, what else you need? Well, remember the 4 steps that I mentioned? Well, that's from the previous lecture. So you gotta show that there's an optimal substructure, and then you gotta show the recursive relationship that gives you the optimal solution. And number 3, you gotta find the value of the optimal solution. You gotta use that recursive relation to give you the value. So the value here is the least number of rows that you need. That's just a value. And the combination, that's the optional step. The combination is the actual rows that will give you the optimal answer. So I think the optimal answer is, not sure, thinking 15 plus 18 rods, right? That is the optimal answer, the value of the optimal solution. But the actual combinations, well, what are the coins? You need 100, and 50, followed by 15 ones. That's a combination. That's step 4. So let's go with step 1 first. Optimal substructure. So just a rehash. A problem exhibits optimal substructure if the optimal solution to the problem can be constructed using optimal solutions to the subproblems. I'm going to do this again because I know we already went through it last week, but well, in my experience, students have problems with this. If you already understand how optimal substructure work, great. Just listen to me for a bit. You understand what's going on, great. If you still not sure about optimal substructure, well, here is another example that we can go through. Okay. So I need to formalize this a little bit to make it easier. I'm just gonna say instead of F is kind of like too simple to use. So I'm going to change the problem into min R, like the minimum number of rods. So I'm going to say that min Rn is the function that returns the minimum number of rods required to construct a rod of length n. Okay, so we want to solve min Rn, and this is the breakdown. If I pick 100, I will have 1 plus min Rn minus 100. What's that mean? I'll pick one coin, like 100. Oh, I keep saying coins again, sorry. I pick a rod of length 100. Then I'm left with a subproblem, which is finding how many rods I need in minimum to make a rod of length n minus 100. So same thing if I pick 50, same thing if I pick 25, same thing if I pick 1. I'm going to solve a subproblem with the input being n minus that rod length. Okay, minus 100, minus 50, minus 25, or minus 1. So does it have optimal substructure? Well, okay. Let's say n is equal to 65, like the problem that, the example that we had before. And suppose that the optimal solution is 18 bars. Well, we say it was 18 bars, like 2 bars of length 100, 1 bar of length 50, and 15 bars of length 1. Which branch gives you this solution? Like, what did you pick first? Well, you can actually pick 1, you can pick 50, you can pick 100. Which one do you pick first? Let's just say that I decide that the second branch is the optimal path. Like I went to min R to 65 and then I go min R to 15. Remember, you know what the optimal solution is. This is how you prove optimal substructure. You assume that you know the optimal solution. Okay. So I know the solution to min R to 65, the original problem. But to get this optimal solution for 265, I also know that I need to solve min R to 15. This one here, let's say going down there. Now, I'm gonna claim that the solution that I use from that, the solution that I get from min R to 15 is also optimal, right? Because the optimal solution is 18, so min R to 15 needs to give me 17. Well, 17, and 17 must be the optimal answer to min R to 15. So that's my claim, that 17 must be optimal. Why? Because if there's a better solution to min R to 15, so let's say 13, then my solution to min R to 65 is just 1 plus 13, which is 14. There is a solution like that, which means that my original assumption, well, I said earlier that, look, 18 was the optimal solution, but now I can actually make one with 14. So no, 18 was not the optimal solution. So no, that's a contradiction. Meaning that if I do have the optimal solution to min Rn, then I also have the optimal solution to min Rn minus whatever I chose to be the best. Whatever is part of my optimal solution. Look, I really hope that makes sense. Let me go through one more time. Sorry, I'm being slow with this, but I really want people to understand how this works. It's really not hard. And maybe I'm overcomplicating this because I'm trying to say something easy again and again and again. So if you think this is easy, you're actually right. This is. But better safe than sorry. All right, I'm gonna generalize this. Again, I have to solve min r. Okay, that's the problem up top here. That's the this guy here. I have to solve that. And to solve min r, I gotta solve the subproblems. I mean, in dynamic programming, I go through all of them. Okay. All right, but if I do have the optimal solution to min r, that means I know which one of these, or which one I use as part of my solution. So I'm going to say, let's say the optimal solution to min Rn uses the optimal solution to min Rn minus b. For some b, I don't know which b, but one of them. Okay, it's just like either I pick 100, I pick 50, I pick 25, whatever. That's the one that I pick, is the one here. And then whatever is remaining on n, I have to recurse. So I claim that the solution, whichever subproblem I use, I've claimed that the solution must be optimal. Because if it's not optimal, then there's a better solution for this, for min r n minus b. And if there's a better solution, then I can make a better solution for min r. So that can happen. So because that's a contradiction. That's impossible. Doesn't make sense. Right? So again, because we keep saying, if min Rn, if the solution to this one is optimal, then it will use the optimal solution to the subproblems. So if min Rn uses min Rn minus b2, then the solution to min Rn minus b2 must be optimal as well. Again, because if it's not, then I can find a better min Rn. Okay, hopefully, yeah, that makes more sense. What about the recursive relationship? I mean, what is the relationship between the problem and the subproblems? Like, which one do we choose? So how do we know which one it will give you the optimal answer? Remember, again, dynamic programming, you go through all of them. You evaluate every single one of them, and then you choose one which is the best. So I got n. If I take 100, I mean, I have to do n minus 100. If I pick 50, I have to do n minus 50, and so on. These are all the subproblems, right? I'm always gonna be doing 1 plus the coins I need to represent the rest of the sum. No, I keep saying coin again. I'm sorry. The number of rods that I need to represent the rest of the sum. So that is the recursive relationship. You go to all of them, right? And you find the minimum. So again, 265, you pick 100, you got 165 left. You pick 50, you got 215 left. You pick 25, you got 240 left. And then you ask, okay, if I got 240, how many coins do I need? If I got 165, how many coins do I need? And you pick the one which is the minimum. Right? So, if I pick 100, you got 165, you need this many coins. If I pick 50, I have like 215, then 215, I need this many coins. You just pick the best one. If you remember the code for rod cutting, this is going to be very, very similar. Okay. Anyway, look, we spent so much time discussing define and conquer, brute force, and dynamic programming. And like, this is actually not for kill. Like, because in these approaches, you go through every single node in the search tree. You go search for the answer everywhere. You don't need to. And hopefully you can already see it. The problem is actually very simple, right? It's just like coins. Like, you gotta pay someone $1.70 and you get all the coins. I mean, you pull out your coins in your pocket, you got all the coins. What do? You gotta pick $1? You gotta pick 50 cents? You gotta pick 20 cents. Done, $1.70. You're not gonna bother with your 10-cent coins. Because why? You got 50 cents, you got 20 cents. Why are you gonna bother with 10 cents? Right? So if I'm gonna make 265, what I want to do, I'm gonna pick 100. I'm gonna pick 100 again. I'm gonna pick 50. That's the best I can do. Can you convince yourself that that's the best you can do? Can you do better than that? No, I don't think so. Right? But why? Can you prove it? You can see it, but how would you prove it? And again, that's what makes greedy algorithm hard. By the way, can you always do this? If you always pick the largest rod that you have, will that work for every problem? How about this one? So I give you 70, 50, 10, and 1. Can you make 100? All right, let's do greedy. Like, what did we do? We picked the largest rod, right? You pick 70. Great, I pick 70. And then what? If I pick 70, I gotta make 30. If I make 30, I need 10, 10, 10. So I need 4 different rods. But is that the optimal answer? No. You got 50 there. You pick 2 50s, you're done. You got 100. So like, what's going on? So can we use greedy or can't we? Well, this is why I say greedy algorithm is the hardest of the bunch. The algorithm is easy. Look, you got a problem, pick the largest one. How easy is that? Just keep on picking the largest one. Yeah. And it's very fast. You don't have to go through every single node. It's very, very fast. You don't have to search, really. You just go down one path. But proving that it works is hard. This is why greedy algorithm is the hardest of the bunch. So I'm gonna stop the video here. So what I've done is we talk about this one problem here. We try to solve it using dynamic programming, using brute force, and finally using greedy algorithm. And you can kind of see that greedy algorithm doesn't really work. We're actually gonna continue this in the in the workshop, I think, because in the next lecture we're gonna focus on greedy algorithm. But I think we're gonna be going through the different problem. But we'll see. Alright, so that's it for this lecture. I'll see you in the next one.